Hi, I'm Antonio Selle, and in this video we will discuss how to compute the distance between two ellipses as an example of using linear matrix inequalities, semi-definite programming tools to numerically find such a distance, as well as an example of the Schur complement formula. Let us start with the end result. We have two ellipses and we wish to find the minimum distance and the points achieving such a minimum distance. And we will use semi-definite programming, LMIs, to do that. So let's delve into the details. First, we'll load the necessary toolboxes, YALMIP and ZUMI, in this case, for instance. And my problem statement is based on ellipses, so well. This quadratic inequality is an ellipse of center C and shape matrix, let's say P, or well, if P is the inverse of Q, I can also express the same in equivalent form. And of course, if P and Q are positive definite matrices, these expressions are equivalent. Otherwise, we may have degenerate ellipses, cylinders, hyperboloids, or whatever, which are not in the scope of what we are going to do. So let us define the ellipses. This will be the center and shape matrix of the first ellipse, and this will be the center and shape matrix of the second ellipse. And Q is proportional to the square of the size of the ellipses. P is proportional to the inverse size. Here we have the ellipses, and the eigenvectors of Q tell me the directions of the axis of the ellipses, and the square root of the eigenvalues of Q tell me the length of that semi-axis. So with different Q, we can have axis-aligned ellipsoid or non-axis aligned ellipsoid if Q is not diagonal, but okay, details on that is not the topic of this video. So we have these matrices, and then we need to pose an optimization problem to get that minimum distance. And we will use what is called Schur formula, that says that if I have this matrix inequality, this thing, and Q positive definite, well, this thing is equivalent to this thing. Of course, proving this is not the goal here. We are using this in our ellipsoid definition as this. This is my ellipsoid, and then if 1 is A, x minus c is B, and okay, this is the easiest, Q is Q, then if the ellipsoid is non-degenerate, Q strictly positive definite, then x is in the interior of the ellipsoid if this happens. And the thing is that this expression was quadratic in x, but this expression here is linear in x. This is a linear matrix inequality in decision variable x. Well, a vector of decision variables is x is if x is two-dimensional, like in this case. The good thing about linear matrix inequalities is that optimizing under this kind of constraints is a convex optimization problem that can be easily solved. But well, solver will require greater than equal, and that's the difference between engineers and math. We engineers say, okay, look, it works, and for mathematicians, okay, it's very different. Open sets versus closed sets, interior, whatever. But okay, we are just in a quick and dirty thing, and we will not discuss this. So I will need a search point in each of the ellipses. So this will be x1, this will be x2. They will be semidefinite programming decision variables SDP var of size 2 and putting this thing for point 1 and ellipsoid 1 and point 2 and ellipsoid 2 is what we are doing here. I start with empty LMIs and I add 2 of them. So we have 2 points in the ellipsoids, and if the distance between 2 points is smaller than d, it means that the Euclidean norm of the difference is less than d, or the squared Euclidean norm is less than d squared. So the Euclidean norm of the difference is this matrix expression, and if I move this transposed by something to the left, I get this thing. So I can again apply Schur formula. D squared is A, x1 minus x2 is B, and in here I can always invent an identity matrix standing for Q in this formula. So I will have here identity, I will have here d squared, and I will have here x1 minus x2 transposed, and here non-transposed. So well, writing that in MATLAB, this is the application of Schur formula that I am putting here. So if there exist points closer than d, then this thing will be feasible. So my optimization problem will be lowering and lowering and lowering d until this constraint, jointly with the 2 constraints that x1 must be in ellipsoid 1 and x2 in ellipsoid 2, well, I must lower and lower this distance until condition C is being feasible, so I will have found the minimum distance. Well, as d squared is not linear, this is not an LMI in d, but it is an LMI in a dummy variable I called d squared, or Johnny, you know. And then minimizing d squared subject to the 3 LMIs, 2 ellipsoids and 1 distance bound, is something that my ZUMI convex optimization solver can quickly do. It took 20 milliseconds and got successfully solved. So d squared was 0.28 and its square root was 0.53, and then with some f implicit to plot the ellipses and getting the value of the points that the solver found and plotting them, well, I got these 2 ellipses and the points that gave me the optimal distance which I was seeking, and they showed at the start of this video. So this is it. Let's just change numbers and do a couple of examples to confirm that this works in other cases. Let me, for instance, move the second ellipse 2 units to the right and change one of the axes, let's say. In this case, ellipsoids intersect, and the code says successfully solved, and the minimum distance is 10 to the minus 15 because, okay, numerical solvers have some tolerances in the solving options, and then up to 10 to the minus 15 power, this is, 0 distance, and the square root is 0 up to our very, very small tolerances. And the 2 points that MATLAB found are coincident, so they are at 0 distance. And well, if I move differently my ellipses or change the shape matrix, here I have different ellipses, and the numerical solver, well, finds another points. So we finish here. In this video, we showed how to numerically compute the minimum distance between two ellipses and the points achieving such a minimum distance. We used LMIs, linear matrix inequalities, and a semi-definite programming optimizer to solve that, because a point in an ellipse was encoded in these LMIs, and the distance bound d encoded in this LMI, so minimizing d squared subject to those LMIs produced the required results. And in fact, the procedure extends to ellipsoids in higher dimensions and also to more general LMI sets such as polyhedra, intersections of ellipses or whatever, which for brevity will not be considered here. So we end the video now. Thanks for watching.